This is lesson 5.6. We are learning how to factor special quadratics. Can anyone tell me, remind me, you don't need to write it down right now, any of the names of the special quadratics that we talked about in earlier lessons? 5.2 I think it was. Any names of special quadratics? Ones that multiplied and made perfect things or made weird binomials?
Perfect square.
We had the word perfect. Perfect square what? Is it a binomial, a monomial, a trinomial, a polynomial? Anybody? It was a trinomial. Any other names? Alright. Which two belong with each other? Hand up. If you think you know two that go together. Paul.
Second and fourth.
Product of sum and difference goes with the difference of squares. Do you agree? Sure.
No.
We forget, Mr. E. Which means that perfect square trinomials belong with binomial squared. Okay, these are all of the special binomials that we've already learned about. We have learned how to get from one to the other. So we've learned how to multiply them. So we've learned how to get from a binomial squared to a perfect square trinomial. And we've learned how to get from the product of a sum and difference to difference of squares. But factoring is the opposite of distribution, right? Factoring is the opposite of multiplication. It's doing it in reverse. So we're going to be able to now go from the perfect square trinomial and factor it into the binomial squared. And we're going to do that by identifying patterns, the same way we did before. So what we're going to do on our notes is we're going to organize these a little bit, and we're going to think about the patterns that were used, and then you have to memorize the patterns, which you already have memorized, thankfully. Okay, your page is split into two columns. Here's what I'd like you to write on the left column at the top. You should be writing the product of a sum and a difference. The product of a sum and a difference. What does that mean? Well, a product is when you multiply things together, and the sum and difference represent what's inside the binomial. So one of our two binomials is going to be a sum, a plus b, and the other binomial is going to be a difference, a minus b. Somebody help me factor this, or FOIL this. Somebody help me multiply this out. First times first, a squared. Outside times outside, minus AB. Inside times inside, plus AB or BA, doesn't matter. And outside, last times last, negative B squared. Now what can I do here?
You can cancel out ABs.
Yeah, this is just minus AB plus AB. Minus 1 plus 1 or whatever it is, you just cancel it out. It's the same thing. So you've got A squared minus B squared. Now, what is this statement called? It has a difference in the middle, and it has squares on the outside. This is a difference of squares. Good. Let's do an example. So going down in that same column, you can maybe draw like a squiggly line. Okay, like these are your notes, right? And on that line that you have in the middle, you can draw an arrow going down. You can now go from a product of a sum and difference to the answer, a difference of squares, just by using a pattern. You can go straight from here to here, just by noticing that you have AB, you have a sum, and you have a difference. Okay, you can skip all the way down to the difference of squares. Let's see a couple quick examples. Should be review, so we'll do just a couple examples. Let's see what happens if we take x plus 1 times x minus 1. What do you notice?
Difference of squares.
Wrong.
Product of sum.
It's a product of a sum and a difference. Okay, good. It is the product of a sum and a difference. So, what's A?
X squared.
Okay, so A is x. What's B? 1. So we know we can skip right down using our pattern. This is going to be x squared minus 1 squared. A squared minus B squared. Now x squared in brackets is just x squared, and 1 squared is just 1. So here we have x squared minus 1. This is now called difference of squares. That's what we just did, right? We went from a product of a sum and difference to a difference of squares. Good. I'm going to
Is
do
that a difference of squares? The other one doesn't have squares.
1 is a square. All our square numbers are 1, 4, 9, 16, 25, 36, right? These are all squares. Good. I can represent it this way. That means it's a square. I'm going to erase this one. We're going to do a little bit more of a challenging example. You could just do like another little squiggly line underneath that one. Hopefully you have room for one more. We are going to do 3c plus 10 times 3c minus 10. What do you see? It is a product of a sum and a difference. There's two binomials multiplied together. They both have the same a, and they both have the same b. One of them are stuck together with an addition. One of them are stuck together by subtraction. That's a sum and a difference. So what can I do here? Yeah, so I could do it all in one step. I really want to show that in-between step though. So A is 3c. That means I'm going to have 3c squared. And what's B?
Negative 10.
What's B?
Oh, sorry, negative 10 squared.
Just identify B. A plus B,
And
A minus B, 3c plus 10, 3c minus 10,
0.
10.
Zero.
It's just 10. B is 10.
I didn't say that.
B is 10. We have a minus sign in front, so we've got 10 squared. Okay? Can you see how this is A squared minus B squared? Now we can do some algebra on it to get our final answer. 3c squared means we have to square the numerical part as well as the variable part. So Isaiah had it right. It's 9c squared. And 10 squared is 100. What is our answer called?
Difference of squares.
It's called the difference of squares. Good job. There's two examples. All right, let's move over to the right side of your chart. And on the right side of your chart, you are starting with a binomial squared. Binomial squared. Well, that means we've got a plus b squared. Right? Can someone help me expand this? What does this look like if we expand it? A plus b squared. Yeah, we're going to have a plus b times a plus b.
No, because it's not.
Good, so let's do the whole step. Let's do the whole step to show how the pattern works again. So now what? If I foiled this, can you guys help me foil this? A times a,
A squared.
outside times outside. Yeah, and inside times inside would be 2ab. Let's just leave it as plus ab for now. That's outside times outside, inside times inside. And last times last, b squared. And we can reduce this by grouping our like terms. We have ab twice, that's 2ab plus b squared. Now, what is that called?
Binomial.
Now, remember there were four that we were talking about? Binomial squared results in a
Perfect square.
Perfect
Trinomial.
square
Trinomial.
trinomial. And again, what we have already done is go from a binomial squared to a perfect square trinomial. Okay? This is review still. Let's do a couple of examples. Let's do x plus 3 squared. What is that called? It's called a binomial squared. It's a binomial, it's got two terms in it, and it's going to be squared. That means if we identify A, what's A in this case? A is x. What's B? B is 3. So at the end, we should, if we just use our pattern, we should have x squared plus 2ab. So we have 2 times x, because x was A. And what was B? B was 3, so we're going to multiply it by 3 as well. And then at the end, we have b squared. So it's 3 squared. Well, x squared is just x squared. 2 times x times 3. 6x, because multiplication is commutative. I can do it in any order I want. I can say 2x times 3, or I could say 3x times 2, or I could say 2 times 3 is 6, times x is 6x. Either way I want to do it, I'm going to get 6x. And 3 squared? 9. What is this called?
Perfect square trinomial.
Perfect square trinomial. Good. I'm going to clear that little example, and I'm going to do another one that's slightly more difficult. This one had an addition sign in the middle. We're going to do one that has a subtraction sign in the middle. Let's look at 3b minus 5 squared. What's this called? Somebody else say it.
Binomial square.
Thank you. Binomial squared. If I use my pattern, I'm going to skip right down to my pattern here. What's A? 3b is A. So I need to make sure that 3b is in brackets and the whole thing gets squared. Because the number part and the letter part both have to get squared. Then we've got 2 times A times B. You've already told me that A is 3b. So I want to make sure that's in a bracket. And what's B? B is not negative 5. Careful.
5.
It's 5. Oh, and actually, we used the wrong pattern. Because if it's a negative sign in between.
Why is it not negative 5?
So what we're doing, okay, personally, I like what you're saying, Vlad. I like, let's leave this pattern as plus, and let's put negative 5 over here. Okay, I like that better. The pattern that we got in 5.2 said to do this. You just use subtraction there, and then you have your 2a, b, where b is just the value, not including the subtraction sign. Does that make sense? So this is going to be a positive times a positive times a positive with a negative in front. So it's going to be negative at the end. This is going to be positive times a negative, which is a negative. So they're the exact same.
Yeah, but the second one will be positive.
No, because there's a minus sign right there.
Yeah, but
So it'll be
Positive,
positive, positive.
that's a negative.
With,
and negative
no,
and negative.
positive is positive. Positive times positive is positive.
Oh.
Right? So they'll both be the same. I prefer this way. This is how my brain thinks about it. The pattern that you've been working with so far says to do it like this. But you may choose. Okay? For the sake of this one, let's do it here. And we get plus b squared at the end. We said b was 5. This is where it gets tricky because b is 5, not negative 5. It again would be the same answer because if you square a negative number, it will just be the same positive value. Okay, 3b squared, Jonathan. Close? Yep, 9b squared. And here, I think I would do 2 times negative 5 first. Julia? Negative 10. Negative 10 times 3b, Emma?
30.
Good. Negative 30b. And 5 squared, Vlad? 25. What's this called again, this trinomial?
Perfect square trinomial.
Perfect square trinomial. Thank you very much. Those are our examples of review. Now what we're going to talk about today is not just being able to go from a binomial square to a perfect square trinomial, or from a product of a sum down to a difference of squares. We're actually going to be able to go the other way as well. So go ahead and draw an arrow at the top of your line as well, because what we're doing today is using those same patterns to check to see if it really is a perfect square trinomial, or to see if it really is a difference of squares. And if it is one of those, then we can just use our pattern and jump right back up to the final step. And that's what our examples are like today. Underneath the line there on your front page, you should have room for a few notes. And really the notes are just what we already talked about. So we already have seen that a plus b times a minus b equals what?
The difference of
A
squares.
squared.
Difference of squares, good. A squared minus
Minus B squared.
b squared. Great. What's also true then is that a squared minus b squared equals what? Okay, so if you ever identify the product of a sum and difference, you know it equals a difference of squares. If you ever identify a difference of squares, you know it's going to be factored into the product of a sum and difference. Okay? This is called multiplying, the top one here, or distributing. The bottom one here is called factoring. So you cannot factor this. This is already factored. But if you see a difference of squares, you can factor it just using a pattern. You just have to use a pattern in order to factor it. Okay? What else did we see? We also saw that a plus b squared is equal to a squared plus 2ab plus b squared, and that a minus b squared is equal to a squared minus 2ab plus b squared. Now if those things are true, what is true about finding this perfect squared trinomial of a squared plus 2ab plus b squared? What's it going to be equal to? A plus b squared. It's going to be equal to a binomial squared. What if we have a squared minus 2ab plus b squared? What's that going to be equal to?
A minus B squared.
A minus b squared. Going this way, on the top, the two examples, is multiplying, or I'm going to use a different word. It's also called expanding. Okay, expanding and multiplying something out is the same. And what's it called when we go from a perfect square trinomial to the binomials? Yeah, but we're splitting this into its dimensions or its factors. We're factoring. And this marker is going in the garbage. Factoring. Good? Now, one of the keys that we're going to learn in our examples is you need to know how to identify whether the trinomial given is actually a perfect square trinomial. If it is a perfect square trinomial, we can represent it like this. If it's not, we can't. Okay, so the first thing we're going to do is say, is the first term squared? Yes or no. Is the last term squared? Yes or no. Is the middle term made out of 2 times a times b? Yes, then perfect square trinomial. No, not a perfect square trinomial. Try another method. Okay? Let's look at example 1. Example 1 deals with difference of squares. Example 1 deals with difference of squares. We're only instructed to factor. We are asked to factor in a x squared minus 100. Don't call out your answer. Do you see a difference of squares? Do you see a difference of squares? If you think yes, raise your hand. What has to be true in order for this to be a difference of squares?
You have to have a negative sign to
Has to be a difference.
And it has to be squared.
A has to be squared, and this has to be a square number. Is x squared a squared thing?
Yes.
Yeah. Is 100 a squared thing?
Yes.
Yeah. Okay, so we do have a difference of squares here. So, what are we going to do? We're going to use pattern for difference of squares. Please write these notes as we go. You're going to use the pattern for the difference of squares. Okay, well, let's recall the pattern. It's a squared minus b squared equals a plus b times a minus b. Okay, well, let's represent our numbers as the squares that they are. So if my first term here is a squared, then I've got x squared. My second term is 100. How could I represent 100 as a number squared? What number is being squared to get 100? Linz? 10 is being squared. So we've got 10 squared. And now all I need to do is apply my pattern. What is a in this case? X. What is b? 10. So all I have to do is instead of a, I plug in x. Instead of b, I plug in 10. Same thing in the next binomial. Instead of a, I plug in x. Instead of b, I plug in 10. I now have the product of a sum and a difference. And that's how you factor a difference of squares. And this is done. Tough? Not tough. Okay? You identify x squared is x squared. 10 squared is 100. That means a is x, b is 10. Plug it into the pattern. Carry on. Okay? B in example 1 is 98a squared minus 450b squared. And we're asked to factor. Now don't get your thinking caught in a rut. What is the first thing that we want to do when we're factoring? What's the easiest
Are they
thing to
even
do
numbers?
right off the bat? We could say, are they even numbers? They are. What does that mean?
You can divide them, factor them out.
That means no matter what, we know we can factor out the number 2. Now, we would factor out 2 only if 2 is the greatest common factor. We want to pull out the greatest common factor. So we want to find out if there's a number greater than 2 that can divide both of these numbers. Does 450 divide by 98? You can just check it in your calculator. 450 divided by 98, it doesn't work. You want to try anything else? 50, does 50 divide 98? Anything else?
4.5.
Would you like to try to divide it by 4?
Won't work.
Won't work. 6?
No.
Definitely.
Okay, let's just stick with 2 and see
Five
where
will
we
work.
get. Okay? This is divisible by 5?
No.
No.
450.
The greatest common factor is 2. Okay? So step 1, remove the GCF of 2. Remove the greatest common factor of 2. Well, that's actually a false way to say it. Just say remove the GCF. Remove the greatest common factor. Alright, if we pull 2 out of here, what are we left with? 98 divided by 2? Almost 50.
48.
49a squared. 450 divided by 2?
250?
I'm not trying.
Good. Now what? Now we need to see if we're dealing with a difference of squares. Well, it's easy to see in the variables. A squared is squared, right? Is b squared a squared value? Yeah, that's easy. Is 49 a square? 49 is a square number. Okay, well, let's rewrite this for a second already. And we're going to use square brackets. What is 49? What's the square root of 49?
7.
Okay, so if we had 7a squared, would we get 49a squared?
Yes.
7a squared? Yeah. 225, does it have a square root? An integer square root?
Probably.
5. No.
Let me check.
Not 5.
Yeah, just throw in your calculator. Square root of 225.
Okay, how do you do that?
25.
Just for the sake of speed, it's 15.
Oh,
And the
shit.
square root of b squared is b.
It's 15.
10 years.
So here's what we have.
Well, it's not squared.
Because there's
Oh,
one.
never mind, it is.
And now if we use our pattern says that we just have, inside this square bracket, we should just have a squared. We should be able to split it up into a plus b, a minus b, right? There's a plus b, a minus b. A is 7a, and b is 15b. So all we have here is 7a plus 15b,
Where's the square?
7a minus 15b. If you really like to keep the squares in there, you may do that for this step, but then you need to do one more step and remove them.
Not the square brackets. The square.
Oh, the exponent to the power of 2. Who can tell us where these guys went?
Into the
Oh, I see. Never mind.
and
Yeah.
Yeah, all the information that's right here is also contained in here.
Yeah.
All we did was use our pattern, and we've proved that it works several times. Okay? So this is fully factored. This is your final answer. A factor of 2, a factor of 7a plus 15b, and a factor of 7a minus 15b. So first, pull out the greatest common factor, then identify whether or not you have a difference of squares. If you do, then you can use your Example 2 deals with perfect square trinomials. So the first thing that we need to do is verify, that means prove or test, to see if what you've been given actually is a perfect square trinomial. So we've been given an a, x squared plus 6x plus 9. And the first thing we need to do is test whether or not this thing is a perfect square. Okay, is the first term a square number? Is the last term a square number? Now, if it is a perfect square trinomial, how does this middle term get built?
Divide by 2.
A times C.
Divide by 2.
Not by 2.
2
But
a b,
wait, what?
right? That's the pattern.
Yep.
A squared plus 2ab plus b squared. Okay, so let's find out if this middle term actually was built from the a of the first term and the b of the last term. Okay? Well, what got squared to get x squared? X. So a is x. What got squared to get 9? 3, right? So c is, b. B is 3. Okay. Let's go 2 times x times 3. What's that equal? 6x. Is that what we have in the middle term? Yeah. Okay. So do we have a perfect square trinomial? Good. We're going to write a little sentence here. Since x squared equals x squared, and 9 equals 3 squared, and 6x equals 2 times x times 3, x squared plus 6x plus 9 is a perfect square trinomial. So, use appropriate pattern. Well, the appropriate pattern for a squared plus 2ab plus b squared is what? Who knows what pattern we're using here? What is that going to be equal to? A plus b squared. So now, bringing this all the way down to here, and using our pattern, we've already decided this side is true. It's a perfect square trinomial. What's A? X. What's B? 3, and we square it. So all we had to do was test, is the first term a square? Yep. Is the last term a square? Yep. Is the middle term built by 2ab? Yep. Okay, use your pattern. There it is, x plus 3 equals x plus 3 squared. Good. Second example, B. So example 2b. Well, we talked a lot before starting. X squared minus 12x plus 36. Let's do this one quickly. Is the first term a square? Yes. What is A?
X.
A is x. Is the last term a square?
Yeah.
Yes. What is B? 6. Is the middle term following some kind of pattern? Looks like negative 2ab. So negative 2 times x times 6 equals what? Negative 12x. So is the middle term built from here? Yep. So what's our pattern? Yeah, we've got, well, close. We've got a squared minus 2ab plus b squared, and that equals a minus b squared. So now all we need to do is go right from our top using our pattern. We've already said a is x, b is 6, and we square it. Done. If you're not sure, you can go backwards and double check. Okay? You now know how to factor a difference of squares, and you know how to factor a perfect square trinomial. Let's do a couple more difficult ones, and then we'll do one real-life application or word problem. So here's example 3. It's just a more complex one. The directions for us are exactly the same as they were before. First, we're going to verify that it is a perfect square trinomial. Then we're going to see if we can factor it. Okay? Ready? Really quick. Emma, is the first term a square number? Yep, because 4 is a square number and x squared is clearly squared. Is 49 Tanner a square number?
Yep.
Yeah, 7 times 7. Okay, so we've got an a of the square root of this. So the square of the 4 is 2 and the square root of x squared is x. We've got a b of the square root of 49, which is 7. So we need to see what 2ab is, right? That means 2 times 2x times 7. Well, 2 times 2x is 4x. 4x times 7 is 28x. So do we have a good pattern here? Yep. So all we need to do is plug it into our pattern. What pattern are we using? A plus b in brackets and then squared. A plus b, I'm not going to write it. I'm just going to put our a in, which was 2x, our b, which was 7, and square it. Good? B is 25k squared minus 60km plus 36m. 25k squared minus 60km plus 36m. Now that looks, m squared at the end there. That looks pretty tough. What are we going to do? Okay, is there a greatest common factor between any of these terms that can get pulled out? No, because we got two even numbers. We got a 25 there. 5 doesn't divide 36. 6 doesn't divide 25. Okay, so let's just see if we have a perfect square trinomial, how we have it, right? So what do I need to do then? Find A and B, right? So really I'm testing to see, is this a square number? Yes, 5k. Vlad, is 36m squared a square number? Yes. What's B?
6.
Anything else? 6m. Good. Now we need to determine this middle term. I see a subtraction out front, so the pattern we're looking for is minus 2ab. Well, if I use our information, that means we got minus 2 times 5k times 6m. I like to do probably 5 and 6 together. That's 30. 30 times negative 2, negative 60, and I've got a k and an m. Did that work? Yeah, so this fits the pattern of a perfect square trinomial, which means the answer is just a binomial squared. A plus b or a minus b? A minus b. Good job. Okay, make sure you're paying attention to that subtraction sign there. So 5k minus 6m squared. That's it. Doable? Barely. I'm sure you can handle it. Okay, cruising on to example 4. Example 4 is just taking what we just learnt, putting it into a word problem. So we've got two ways to do it. And I might show you both ways if we have time. So area of a region. You have the pictures of the squares there? Okay. The one square is represented by side lengths 3x plus 8. And the other square is represented by side length x minus 2. But we're talking about the area of the square. So we're finding an algebraic expression. That just means a number sentence with variables and numbers, addition and subtraction. An algebraic expression for the area of the shaded region. Oh, so what are we really talking about here? What's the goal, you think? We're getting the area of the shaded region. Can someone describe to me the shaded region? Is it the whole thing? Is the whole picture shaded? No.
There's a little square taken.
There's a little square taken out of it. So could you say it's the area of the big square minus the area of the small square? What do we know about area? Area is side times side, which in a square means you're squaring. And we have a subtraction sign. So do you think we might have the difference of squares here? Maybe. Probably. Okay, let's figure this out. What's the area of the big square as an algebraic expression, Vlad? Keeping in mind it's side length times side length. It's on your paper, not on my forehead. The area of the big square, the side length is 3x plus 8. Pardon? Well, we got a side length of 3x plus 8 and a side length of 3x plus 8. How do we calculate the area of this thing? Yeah, we times them together. What's 3x plus 8 times 3x plus 8? Let's go with 3x plus 8 squared. Yeah? 3x plus 8 times 3x plus 8. And the small circle, sorry, the small square? X minus 2 squared. That's how we get the area of a square, right? We just take the side length and square it. Good. So now what we can do is we could expand this whole thing out, do all of our multiplication, and then group like terms, and we'd get an expression. The other way to do it is use our difference of squares. Which way would you like to do it?
Difference.
Do you want to use the patterns that we've been using?
Harder way. Yeah.
Well, let's use the patterns, okay? So our patterns say, look at this. We've got a square value here. What's a? 3x plus 8. Because it's the value that's being squared. So what needs to get squared in order to get x minus 2 squared? X minus 2. Okay? So a here is 3x plus 8. B is x minus 2. And we have a pattern of difference of squares that says we can go straight into, maybe I'll just write it first, we've got a squared minus b squared equals a plus b, a minus b. Right? That's our difference of squares, changing into a product of a sum and a difference. Let's plug in our values into here now, right? We already have this. This is right here. Now we've got a plus b. We said a is 3x plus 8. And we're going to add b, which is x minus 2. And in our second bracket, we've got a, which is 3x plus 8. So I'm going to add a couple brackets in here for us so that we can keep it organized. Minus b, which was x minus 2. So far it's been a little bit tricky just copying in what we have. We just had to identify a is right here, b is right here, copy them in carefully, keep your brackets. Now we get to group some things. Okay, we get to group some things and put it all together. They're just attached by addition in this first bracket here. They're just attached by addition. So in the first bracket we've just got 3x plus 8 plus x minus 2. Now how is that going to be different from the second bracket? What's tricky about the second bracket? Yeah, the second bracket we have this minus out here, which is going to attach itself to this x and this minus 2. So when we take that bracket away, we need to be careful. First bracket is easy, 3x plus 8. But now we're going to have minus x and plus 2. Good job. Minus negative 2. Alright, you guys, this is attached by multiplication now, right? Should we FOIL this whole thing right now?
No, first simplify.
First, let's group our like terms, right? We've got 3x plus x, 4x, and 8 minus 2. And actually, we're not even going to have to do anything else. And in the second bracket, we've got 3x minus x. 2x? No, sorry, 2x. And 8 plus 2. And we're done.
You should have to FOIL.
We don't need to FOIL because that would be just going back up to here. Okay? So this is the goal. There's one thing that you should note that you can take out of all this yet. You see anything you take out of this?
6 and 10 and 4x.
Common factor of 2 in all of these.
So when are we going to our assignment and all that stuff?